Well, there's a famous saying that information is physical. So there is actually no system that is just zeros and ones. Even in your computer, zeros and ones are contained inside transistors. But here, that information is much more tenuous.
You can kind of think of it as, you're wanting to stay within 0 and 1, and this valley splitting is kind of like guardrails, right? And the bigger that valley splitting is, the more guardrails you have to not crash, right? For more or less, yeah.
Hi, I'm Stephanie Whitehorse, Director of Intellectual Property at WARF. I had the pleasure of working to help patent this Innovation Award nominated invention. If you have a UW-Madison invention you'd like to disclose to WARF, please reach out to me directly or at the link shown below. And now, more information about our nominee.
My name is Mark Friesen. I'm a research scientist at the physics department at UW-Madison.
Hi, my name is Benjamin Woods. I'm a postdoctoral researcher in the physics department at the University of Wisconsin-Madison.
The problem that we're solving is related to quantum computing. Quantum computing is a technology that can be used to solve certain types of problems that are too big or too difficult for a regular computer to solve. Our group works on the hardware side of quantum computing. We work with materials of silicon and germanium, and we build tiny little devices called quantum dots that are actually quite similar to transistors in your computer or in your phone. So the key issue here is that these devices are not just abstract zeros and ones. They're actually physical devices. And those physical devices have states which are not just 0 and 1, they have states which are also excited states, and if the qubit accidentally goes up into one of those excited states, it's very difficult to get it out. And that causes an error for the quantum computation.
So you could have 10 spin qubits in your array and one of them won't work. And if you're trying to make a large-scale quantum computer with that, that's just a no-go, right? So in a qubit, you always want to have two isolated levels that are representing 0 and 1. And the problem in silicon spin qubits is that there's some peculiar features of silicon that make it so there's additional states that qubit can be in, right? Besides 0 and 1. If the energy spacing between your 0 and 1 and these excited states is not big enough, then that can cause errors in your quantum computation because your qubit can get excited into those additional excited states that you don't want. And so our invention is about increasing that energy splitting. It's a modification of existing technology in the fact that you have what are called silicon quantum wells. And then we're adding two ingredients that are normally not there. So the first ingredient that we add is called shear strain.
Shear strain it means to simultaneously strain the crystal in two different crystal axes. And it causes a symmetry, a fundamental symmetry to break in our silicon crystal.
And the second ingredient that gets added, these germanium concentration oscillations, where you're adding a small amount of germanium into the silicon quantum well. So basically, in conventional type silicon quantum wells, it's just pure silicon. And then what we're gonna do is we add a little bit of germanium into the quantum well, and we call it wiggles because we wiggle the concentration.
However, because we've now modified the silicon crystal by applying shear strain, those concentration oscillations don't need to be nearly as short wavelength. As a result, it's actually something that we can grow in the laboratory, and it's something that we have grown in the laboratory, and we're currently measuring devices with these long wavelength germanium oscillations.
So one of the problems that companies have who are trying to build these quantum computers with spin qubits right now is they have low valley splitting, and it varies from device to device and dot to dot. Valley splitting is as much a concern with them as it is with us. And so they could potentially be interested in this technology.
It's quite remarkable that this silicon crystal, which we thought we knew so much about, actually can be manipulated in this way such that it has these new properties which include this larger energy splitting. And so in the next few years we're going to be thinking about building better qubits, performing better qubit gate operations based on this proposal.
Hi, I'm Emily Bauer, Director of Licensing at WARF. If you like what you've heard and want to learn more about this high potential technology, please get in touch using the information on your screen and in the description below. And don't forget to like and subscribe for more great videos from WARF.